Okay, a very good morning to all of you. I'm sharing the QR code. Give the QR code and we will start. QR code is visible?
Yes, ma'am.
Okay, give the QR code and we will start. Okay, so let us start. I think everybody has given the attendance. 10 students are present. Okay, fine. Sharing the Okay, so yesterday I told you a general base equation. Okay, general equation for the AC bridges, right? So I discussed the general equation for AC bridges. Acha, wait.
मैम
Yes, bolo.
मैम जो हम लोग पढ़े थे मैम कल एसी ब्रिज, तो मैम वैसा ही मैम डीसी ब्रिज का भी रहता है क्या मैम कंडीशन?
वो DC bridge is mainly depend upon Wheatstone bridge. जब कराया था Wheatstone bridge तब कुछ conditions पढ़ाया था ना, वीडियो
हाँ मैम।
चेक करो. हाँ, देखना वहां पे भी कुछ है आर बाई ऐसा कुछ, मतलब कैसे तुम Wheatstone bridge का टर्मिनल्स लोगे, अकॉर्डिंग टू दैट यू हैव टू बैलेंस द आर्म. जो हमारा आर्म्स रहेगा, हमारा 4 आर्म्स होता है हर ब्रिज का, तो बैलेंसिंग वाला जो कंडीशन है वो हर एक ब्रिज में होता है, चाहे एसी हो चाहे डीसी हो. ठीक है, एंड इट वैरीज. हाँ, इट वैरीज. अब गैल्वेनोमीटर जो हम लगाते हैं डिटेक्टर इन केस ऑफ डीसी ब्रिज, तो थोड़ा उस पर वैरी करेगा कि उसमें करंट फ्लो कर रहा है कि नहीं. दैट इज डिफरेंट. एंड डीसी ब्रिज और एसी का भी डिपेंड्स अपॉन द डिटेक्टर, बट द बैलेंसिंग कंडीशन is there both in case of DC and AC. तो DC का जो Wheatstone ब्रिज और केल्विन का जो मैंने पढ़ा था, वीडियोस अपलोडेड है, तो जाके चेकआउट करो कि क्या हुआ, उसमें क्या कराया था मैंने, तो वहां पे मिल जाएगा तुम्हें. ठीक है,
ओके ओके, थैंक यू मैम.
हाँ, थैंक यू. अच्छा, come to the Maxwell. Okay, so yesterday we discussed the general equation for AC bridge. Today we will go to the Maxwell. Okay, so come to the Maxwell bridge. Now, first of all, main question comes: what is Maxwell? This kind of bridge, why we use? Okay, so first thing which you need to remind, that is, need to keep in your mind that Maxwell is used to measure unknown inductance. It is very important. Okay, so don't mix it up with the other bridges. Actually, if in AC bridge we learn 5 to 6 bridges, that is Maxwell, Hayes, Shering, Anderson, De Sauty, Wiens, every bridge has its own measuring parameter. Okay, that means in Maxwell, you see in this particular picture which is given, you can see that there are 4 arms provided, that is R1, R2, R3 and Rx1 is given, and a capacitor is also given. So that means you need to measure the unknown inductance here in terms of a known capacitance. So capacitance will be provided to you, okay, and the resistance will be given to you. So and you have to calculate the unknown inductance here. So where is the inductor connected? You see here with the arm Rx, that is unknown Rx, inductor Lx is connected. And see here with this R3 is the variable resistance. This is R1 is also variable resistance. And here with the C1 we have connected the R1 parallel to C1. So don't get confused. You can also, in this particular section, you can also draw like this. Means in the outward portion, you can put the capacitor inside the resistance. You can also do. Only the connection has to be like this. Okay. So, and you need to provide the unknown, definitely unknown inductance, and that inductance you have to find. Okay. And what else? And you have a capacitor. Now see, I have taken R1 as variable, and across that I have connected C1 capacitor, which is known to me. Okay, now this is not universal circuit. You can also change it like this. Suppose the circuit can be also like this, that you connect your R1 with L1, unknown inductance, and here with R2 or R4 you connect the capacitor. Okay, so that depends upon you, that how you draw the circuit, and according to your circuit the equation will come up. Okay, so I have considered this kind of circuit where I have taken the R1 as a variable resistance. With that capacitor C1 I have connected parallel to it, and inductance Lx, okay, and Rx is unknown to me, so that I need to calculate. Clear? Now, this Maxwell definitely is a modified version of Wheatstone bridge, okay, which is used to measure. Here I can say this Maxwell is used to measure the self-inductance of a circuit. Unknown inductance you can also refer as self-inductance of a circuit, okay. Then comes a Maxwell bridge uses, here see what it's using. It's using a null deflection method. Okay, you see here detector is there, and that is why this kind of bridge or is used to calculate the unknown inductance. And when calibrated, when the calibrated components are a parallel capacitor and resistor, you see here R1 and RC1, these are calibrated components. Okay, they are known as Maxwell bridge. Now, working principle is what? That the positive phase angle of an inductive impedance can be compensated by the negative phase angle of a capacitive impedance when put in opposite term. One thing you notice here, when the C1 is in one arm, the unknown inductance is just on the opposite arm. Okay, it is not sharing the same terminal. Okay, so it should be always on the opposite side. Okay, and the circuit is at resonance. Resonance means no potential difference across the detector. Okay, and so no current will be flowing through it. Now, unknown inductance then becomes known in terms of this capacitance. Okay, so here I told you, just look into the picture as I have taken. You can also change it accordingly, but you have to make sure that you put the capacitor and resistor just in opposite term of the unknown inductance and the resistance. Okay, so Maxwell bridges are again of two types: inductor, capacitance, that type of work there. But here you mainly focus on the single Maxwell bridge. Okay, so now let us see. Achha, one of the yesterday, what formula we have learned? What are the formulas we know? Tell me the formula. I mean, what is the balancing equation we know? Tell me the balancing equation for impedance. What? Z1, Z4 is equal to Z2, Z3. Right? This is my balancing equation for AC bridges. Z1, Z4 is equal to Z2, Z3. Okay, so it is constant for all the bridges, all the AC bridges that we will have. So this is impedance. In case of admittance, it will become Y1, Y4. Okay, that will be equal to Y2, Y3. So I think this much thing is clear to you all. That's the balance equation of the general basic equation for AC bridges. Okay, now you see here in this figure, the ratio arm has parallel combination of resistance R and the capacitance. Okay, so here R1, C1 are parallel to each other. An unknown arm is having unknown inductance Lx and resistance Rx. So see here, this is the unknown part. This Lx is the unknown part and this Rx is the unknown part. Okay. Now, the balance condition of the bridge can be given by, what can we write from this particular diagram, the balance condition? Can you tell me? See, we know R3, with R3 nothing is unknown, R2 nothing is unknown, and with R1 nothing is unknown. So which is unknown part? The unknown part is the Rx. That is, I think, the R4 part, if you say. Okay. Okay, so you see here, I'm connecting the Z1 ZX equal to Z2 Z3. So here ZX is the Z4. Okay, in my, if you follow the this balance equation, so it's here Z1 Z4 equal to Z2 Z3. So here my unknown resistance is Rx. So I can take the unknown admittance, sorry, unknown impedance as ZX. Okay, so what I have taken. Now you see here, wait. Okay, now look into this equation. So this is the equation I obtained. Z1 Zx equal to Z2 Z3. Okay, so from here you can write now what is Zx. So there's Zx will be Z2 Z3 divided by Z1 divided by Z1, and 1 by Z1 is again Y1, means it is the admittance. Okay, so indirectly I can, directly I can write Z1 Z2 Y1. Okay, so don't get confused from where this Y1 came. Actually 1 by Z1 is equal to Y1. That is why I have written Y1 here. Okay, that is why I told you that do remember both the equations. So now you see here, the bridge is balanced by first adjusting R3 for an inductive balance, and then by adjusting R1 for resistive balance. Yes. Now you look into the diagram. Here you see here, here in case of what are the two variable resistance? See, the two variable resistance are R1 and R3. So we are telling here that the bridge is balanced by first. So first we have to, and see, we can adjust those resistance which are variable. Okay, देखो जहाँ पे ये arrow sign नहीं है, that means we cannot vary that resistance. Suppose in case of R2, ठीक है, R2 we can't vary, we can't adjust like this, but R3 or R1 we can, because the variable one. So see here, we can adjust R3 for inductive balance, because here across the R3, same terminal who is sharing this unknown inductive part. Okay, they are sharing. So you have to look into that. And R1 is already having a capacitance. So here R1 can be adjusted for the resistive balance. Okay. Next, you see adjustment of R1 disturbs the inductive balance and R3 needs to be modified. Accordingly, R1 is also modified. So this is again you see R1 actually is opposite to the unknown inductance. So according to them, the adjustment, the following the adjustment that disturbs the inductive balance here, according to them, inductive balance, and then what R3 needs to be modified, accordingly R1 is also modified. So we have to see the modification what they have done. Okay, so picture will be similar. This picture is same. The circuit will be similar. Okay, only just you have to check where the where the resistance is there, and where the unknown inductance is there. So in this circuit, remember one thing, that the R wait. Yes. Okay. Now simple, we will replace these equations with the balance equations. So see here, the process gives a slow convergence and the balance slowly shifts towards the actual null point. This type of balance is called sliding balance. Okay. Sliding balance is a term that we use here in case of Maxwell. Actually, we need to balance, our main motto is to balance the equation to somehow. Okay. So what we are doing first, the actual null point is obtained after few adjustments. Then we need calibration. Now, when you are performing the experiments on instrumentation on this kind of bridges, if you come to see the kits of these bridges, तो देखना कि adjustment हम करते हैं बहुत बार की readings लेने के बाद. We need to do any few adjustment. We need to do various calibrations. We need to slide, मतलब हमें चेक करना है कि नल पॉइंट से कितना दूर में हमें अच्छा रिजल्ट मिल रहा है. We have to check every time. Okay, and nowadays all are kit based experiment to know. So see how the impedance we can write for various sums. Suppose for y1 they have taken y1, you know y1 is what? Y1 is the admittance. Okay, that is equal to 1 by z1. So z1 is actually r1. So r1 plus the imaginary part they have taken, that is j by x1. Okay, so 1 by r1 plus j omega c1 we can write, because we already having a capacitor with this, with r1. Okay, so r1 will be this kind of complex term. Then comes j2 is r2, it's okay. R3 is again Z3. This is also okay. And the next one is the unknown inductance. So whenever you see capacitance and inductance are added, we have to change the formula like this. So Zx will be Rx plus JXL. XL, you know, it's omega Lx, because Lx is the unknown inductance. Okay. So Rx we can replace also like this, that Rx is equal to J omega Lx. That will be equal to what? I mean, how they are equating? They are equating that Zx is equal to, sorry, in the previous day I told you the formula, na? Zx is equal to Z2 Z3 Z2 Z3 Y1. Okay. So in this formula you have to put the equation. So see, likewise we have done. We have replaced the Zx with Rx and this, Z2 with R2, Z3 with R3, and in place of Y1 we have put this particular formula. See, this we have put. And we are just solving this equation. So we will try to equate only the real parts of our equation. Real parts, the imaginary part means the part with J. That's the imaginary part. Okay, in mathematics we have done this. So we will try to equate only the real part. That is, suppose here Rx, it's R2, R3 by R1. So see here, we will just equating the real parts. So after equating the real part, let us see what they have done. See, after equating the real parts, we are getting this kind of equation. That is, my unknown resistance will be R2, R3 by R1. And then I will again equate the imaginary part separately. Okay, so if I do that, this G omega will cancel out. And definitely I can obtain Lx is equal to R2, R3, C1. So everything based upon this equation. So you get two terms depending upon the, after equating the real term and the imaginary term. So from this particular thing, I think two conclusions we can have, that we got two balanced equations, right, that are obtained by equating the real and the imaginary part. This means for an AC bridges, both the relation, that is the magnitude, and the phase must be satisfied at the same time. Okay, and both the equations are said to be independent if and only if both the equations contain different kind of what variables we are using, and that variable can be inductor or resistor. And above equation are independent of frequency. You can see that means we do not require exact frequency of the source voltage. Okay, and also the applied source waveform need not be perfectly sinusoidal, because these things, I mean, as we are not considering the frequency, we are independent of that, so we can do it accordingly, and accordingly what we want, what based upon the calibration and based upon few adjustments. Okay, now definitely there are some limitations of Maxwell bridge. Okay, it is important, and I told you Maxwell are of two types. One is inductor, one is inductor capacitance. So mainly here we I think we have done inductor capacitance Maxwell. Okay, because in my picture you can see here, if I take you to the top picture, that is the why inductor capacitance, because you see here a known capacitance is given and unknown inductor you have to find. So this kind of circuit is known as Maxwell inductor capacitance bridge. Okay, now see what are the limitations of Maxwell. Let us see that. The limitations of Maxwell, this is not suitable for determination of self-inductance of coil. See, I told you in the beginning that it is used for determining the unknown inductance and self-inductance also, but it has a condition. What is that condition? Is that it is not suitable for determination of the self-inductance of coils having quality factor Q less than 10 or Q less than 1. Sorry, Q greater than 10 and Q less than 1. So it is important. So you have to maintain the quality factor of the coil, and you have to also check that it can only determine the self-inductance of the, it is not suitable for determination of self-inductance of the coil whose quality factor is greater than 10, or you can say less than 1. Now it is suitable for the coils having Q values in the range. So this is the range, okay, that has to be 1 less than Q less than 10. If it is between this range, then it can measure the self-inductance of that particular coil. Now this is because the high Q coils, the phase angle is very nearly 90 degrees, okay. So this requires a capacitor having phase angle very nearly equal to 90 degrees. These are some of the limitations in case of Maxwell. Okay, and this situation demands that R1 should be very large, which is impractical. Now, see, there are four arms in Maxwell, right? As I told you. I mean, you can see also there are four arms in Maxwell: R1, R2, R3, R4. None of the resistance can be, I mean, there should not be a very large mismatch between the resistance. I mean, R1 is very large, R2 is a bit small. Okay, we can't take resistance like that. It should be even not same, but it should be not even of so much difference. So agar hum situation mein, if any situation, if they wants that R1 to be very much large, this doesn't happen. So Maxwell ka ye sare limitations hai. The first is it has to check the quality factor of the particular coin, okay, where which it should measure. That is very important thing. And we have to also check the phase angle, okay, phase angle also. And thirdly, the R1 should not be that much large, okay, because if we make it large, which is becomes impractical. Okay, so these are some of the limitations of Maxwell bridge. Now see, we will study many bridges. Now, a question, one thing make in your mind that definitely the bridges have some limitations. That is why we go for the next bridge. Okay, so so this is one more thing is that Maxwell inductor capacitance bridge is very useful for the wide range of measurement of inductor at audio frequencies. Okay, so audio frequency पे हम लोग ये वाला Maxwell bridge बहुत use करते हैं. Okay. Acha. One more thing, phasor diagrams sometimes come with the bridges. So that phasor diagram, now I have not shown here. Okay, let me complete this, then I will share the phasor diagram with you. So just a second. Let me see that phasor diagram picture I have or not. Wait, 2 minutes. Give me 1 minute. Phasor diagram, we can, no, here also they have not written phasor diagram. Okay. Wait for a sec. Sharing, and then high resistance. AC braid, general equations, sharing. Yeah, in this they have. Okay, we are discussing about Maxwell, right? Yeah, Maxwell inductance, Maxwell. Okay. Maxwell inductance capacitance. Okay. Phasor diagram we will do in the next class, only phasor diagram. Then we will not get confused. Wait, let me share again. आज phasor नहीं करेंगे, ठीक है? Okay. Next, if you are asked for, what we have done Maxwell inductance capacitance, right? अच्छा, अगर मान लो they ask you for only Maxwell inductance bridge, then what will happen? Only Maxwell inductance. Then we don't need any kind of you can say capacitance in that particular circuit. Okay, so our diagram, this diagram of particular Maxwell will get changed. Okay, how it will change? Let me tell you that thing. Pushing, just nothing. We will have with this capacitance will not be there in that case. Okay, in that case, and you will be having only simple two inductance. That is, suppose let me share my whiteboard. There I can tell you. Suppose if we are concentrating on Maxwell inductance, then what kind of structure we will be having? Okay, suppose this is my R1. Here you will be having inductance. Okay, and here is your R3, and then again you will be having here R2, and again your inductance, okay, and here R4. So this kind of structure you will be having, and here a detector will be there called D. The detector will be here, okay. This is a structure to just bear because resistance of okay, let it be whatever. Okay, so this is my R1, this is my R1, this is my L1, okay, and you can also take it as R3, and this is my, okay, let me do the connection first. So this is my supply, some supply I'll give here, and here the connection ends. Here like this the connection will end, okay. So this is the A point, this is the B point, B point, this is the C point, this is the D point. Okay. So R1, this is R3 I have taken, this is R2, which is a variable. So I'm putting an arrow here, and this is the R4. Okay. So here this is the L2. So here the current is flowing how? Through this area, I1 will be flowing, and through this area, I3 will be flowing. Okay. And through this area, again, so likewise the current will flow. This is the direction of the current flow. Now in this bridge, you can see arms BC and CD are purely resistive, right? Arms BC, which is the BC arm, you can see here. Wait, let me annotate with other color. This is BC, this is B, this is C. So arms BC, this one, as well as CD. Which one is CD? This one. That means we have no other components connected to it. So we have only pure resistance. So I can say that in this bridge, the arms BC and CD are purely resistive. Okay. While the phase balance depends upon arms AB and AD. This is the another phase balance arm. This one AB. This is A, this is B, and this is A, this is D. So here, as I told you, that this L1 is what? L1 is the unknown inductor for R1. Okay. And here L2 is the variable inductor of resistance R2. Okay. So that is why, sorry, here also you have to put a arrow sign to make understand that L2 is the variable inductor for the resistance R2. So whenever you see this kind of arrow on any kind of resistance or inductor, you will write that variable. The word variable comes. Okay. For L1, I haven't used the word variable. It is the unknown inductor for R1. And R2 is the variable electrical resistance also. Okay. So in AC bridges, according to balance condition, we have a balance point, right? So in that case, we can write, suppose for L1, I can say that L1 is equals to R3 by R4 L2. I can write this equation. And R1 I can write R3 by R4 R2. Sorry, wait, here small r it will be small R2 plus R2, capital R2. Okay. So this equation is according to the balance condition. We have a balance point. So we can vary the R3 and R4. This one, R3 and R4, we can vary it from 110 ohm to 10,000 ohms with the help of any kind of resistance. Okay. So this is the Maxwell induction bridge. So let me tell you another thing. Wait. Just a second. My internet is a bit slow. Okay. So Maxwell, more or less, the bridge formula I have discussed. Quality factor that I told you that why we are using. See, if in your exam time, if you are asked that Maxwell bridge, so we mainly concentrate on the unknown inductance with the using variable standard capacitor. Okay, so if they haven't mentioned, so if they haven't mentioned, then you strictly go for this the previous one which I told you, inductance capacitor bridge. Okay, but if they mention, then you have to do accordingly. So if mainly bridge circuit for Maxwell, we know about that with capacitor. Okay, without capacitor, we can't imagine. I mean, we can't. And then actually, we don't do it actually. Okay, and Maxwell, for Maxwell, the phasor diagram. How? Let me show you. For we have two phasor diagram for Maxwell. One is definitely the inductor. That is the Maxwell inductance bridge phasor, as well as the Maxwell bridge with capacitor and the resistor. Okay. So now I will show you the, as I told you that we have two types of Maxwell bridge. So acha, phasor we will show tomorrow. Okay, in my next class. Now before going to advantage of Maxwell, I told you at balance condition, Maxwell bridges, they are independent of the frequency. It helps to measure, these are all the important point. Okay, the value of audio and power frequency and high range of inductances, all these. Disadvantage, you can say that the fixed capacitor in Maxwell bridge may create some problem in between the resistances. It's not suitable to measure high range of quality factor. Okay, that I told you that the range should be between the range should be between 1 to Q. Okay, 1Q to 1 to 10. This is the range. And the variable standard capacitor we are using in case of Maxwell, that is definitely costly. And it is also not used to measure any kind of low quality factor. Okay, applications you can say, now we can use in communication system, electronic circuit, audio frequency circuit, then different type of power conversions there we actually use. Okay, then this kind of some things are there definitely for which purpose we are using the Maxwell bridge, that we should remember. Okay, Aja, can anyone tell me the formula of self-inductance? Because I have told you that in Maxwell we measure the self-inductance. The self-inductance part you have already studied in your physics, class 11, 12 physics. So can anyone tell me what is the formula of self-inductance? Do anyone know what is the formula of self-inductance? If yes, then tell me. If no, then it's okay. Do you know the formula of self-inductance or you forgot? याद है formula of self-inductance?
मैम माइनस एल di/dt.
Minus L di/dt. The formula of self-inductance is L equals to, okay, N, the flux, the magnetic flux, I'll check, that is phi m, okay, and phi m divided by I, that is the current flowing. So the magnetic flux, when flux is known, the formula of self-inductance should consist of flux also. Okay, so L is the self-inductance in Henry, and here N is the number of turns, and phi m is the magnetic flux in the coil, and I is the current. So this is the self-inductance formula. Okay, at least you tried. Very good. So this is the formula of self-inductance. L equal to N phi m by divided by I. Okay, this is just a basic knowledge, because as we are discussing that Maxwell is all about the self-inductance. That is why I told you. Okay. Okay, so we are not complete with Maxwell. In my next session, I will discuss the phasor diagram of Maxwell with you, both for the Maxwell inductance as well as Maxwell inductance capacitance. And if any problems, we can solve. Okay, so any query up to this portion, then you can please ask me. Any query up to this portion? The phasor diagrams are a bit difficult one, so that's why I will take it a separate class on phasor diagram. Because drawing phasor that you may face a bit difficult. So phasor diagram we will take it in a separate class, but your work will be completely doing this, practice this pictures, this circuits. These are important. Okay, unless you do the practice, then you won't be able to understand the phasor. That is the thing. ठीक है? Okay. Acha, one more thing. Let me share the QR code with you once who are apps who came late. And if you have any query, you can ask. Sharing. Okay. And if you try to segregate or separately understand the Maxwell inductance bridge advantage, disadvantage, then same thing comes. Okay. No, not much difference. Okay. So difference between Maxwell inductance and inductance capacitance, I hope you understood. Okay. One is having capacitance in this picture, one is not having. So that is free from the capacitance. So that is important thing. Okay. Okay, so do this pictures, do this, practice this at your home because this will help you when we will solve the that phasor diagram. Okay. And we have many bridges. This is the starting Maxwell. Then we have Hayes. Then we have Sharing. Then we have at the Anderson, DSOT. Many bridges are there. Okay, then, if you are done with your attendance, you can leave the class. Thank you so much and tell your other friends to also join. Only 12 students are there. So this is not good, right? So tell your other friends and do practice the diagrams. Okay. Okay. Then after giving your attendance, you can leave the session.